Now, in order to create various complex load scenarios at a frequency of 3 GHz, we have used SMA connectors and Rogers 4350 ceramic substrate in order to have a low loss coaxial transmission line loads. We have created a short, we have created a open, we have created a 100 ohms resistive, we have created a 25 ohms resistive, we have created a 50 ohms resistive load. We have created 50 plus J50 comprising of a capacitor and inductor in series with 50 ohms. We created 50 plus J50, 50 minus J50, 25 plus J25, 25 minus J25. We have created open stub, we have created short stub, we have created purely capacitive, purely inductive. So various combinations of these loads are being provided, which allow us to take the measurements in the Smith chart in various quadrants of the Smith chart by trying to simulate all the conditions of measurement. Now, in order to do the measurement, we'll take up few cases. The case right now is 50 plus J50, which is a inductive load, inductor which is made to be in series with a resistance of 50 ohms. So we have replaced the short and we have connected this 50 plus J50. We have noted down the position of the minima by using the short. So the short basically defines the reference plane at which the impedances are to be measured. Since the frequency is 3 GHz and the guide wavelength is about 60 millimeters, we need to be accurate to lambda by 20, which makes it about 2 to 3 millimeters. Our position of the loads has to be precise to the tune of 2 to 3 millimeters. Since these are lumped components, we need to be very precise in trying to know the exact position of the phase where the measurements are to be made. So we have attached a unknown load, and as we move the probe on the slotted line, we see that the voltage keeps on changing. So we will start by taking the probe to the initial position of the short. The short was at 217 millimeters. From 217 millimeters, we will take the probe towards the generator and we will try to measure the distance of the shift with reference to the short. So as you see, as I move the probe, we have a voltage minima, and we are able to get a minima at a distance of 199 millimeters. So that makes it a shift of about 18 millimeters with reference from 217 mm, which was the position of the short. So the shift in minima is 18 upon 60, which is about 0.3 lambda. So we can go on the Smith chart and we can move from the Smith chart and we can point the position of the complex load. We need to find out the voltage maxima at various positions. We need to find out the voltage minima. We need to create a SWR circle, and the shift in minima will give us the exact position of the complex load. If we change the complex load from 50 plus J50 to 50 minus J50, now we have a capacitive load which will be formed in the lower hemisphere of the Smith chart. As you can see, as I will show you on the Smith chart, in the given Smith chart, as you can see, we have the short being placed around this region. The lower region of the Smith chart is the capacitive region. This is the open circuit. At the center we have a characteristic impedance or 50 ohms. The top hemisphere is the inductive load. So you can see different loads can be plotted over different regions of the Smith chart. If we had to be measuring 50 plus J50, we need to start the measurement from the short, and 0.3 lambda will take us, 0.25 lambda will take us around this half of the semicircle, and 0.3 lambda will allow us to plot the complex load in this region. If we had 50 minus J50, our shift in minima will be of the order of 0.1 lambda, and the region where the complex impedance will be in the lower part of the Smith chart. In the same manner, different complex impedances of different values can be plotted on the Smith chart using shift in minima technique.